Alright, so in this video, we're going to go over section 4.3, which talks about L'Hopital's rule. And then this figure right here is just a little review of some limits involving powers of x that we saw in previous sections. And so just a little refresher, for example, if we have a function like this, 1 over x, and if our denominator x is getting smaller and smaller, we have 1 over a big number, 1 over a small number, and so our limit is approaching infinity. And if we have 1 over a super small number in the negative direction, our function's gonna, or this limit is gonna approach negative infinity. Similarly, if we have this kind of function here with a constant on the numerator and a power function in the denominator, we see some similar behavior. In this case, if we have that our function is approaching 0 from the left, it's not going to change the sign of our limit because we have this square here. Additionally, we saw that if we have this function here with the numerator on the top and then our denominator is getting bigger and bigger, we saw that this limit is getting smaller and smaller here. Okay. So we saw all of this in previous sections. And these limits can be easily extended to functions of this form or this form in here. And so this is an example of that. In this first one, we again have this rational function here with a constant in the numerator. And in the denominator, we see that as x approaches 2, this number is going to get smaller and smaller. And remember, we saw that when this number gets smaller and smaller in the denominator, our limit's going to approach infinity. So that's what we get here. So this is, so we're comparing it with this limit here. We see the same behavior. Similarly, if we have this function here, we still have a constant on the top, and in the denominator, we'll see that this denominator is getting smaller and smaller in the negative direction. So if we were to plug in a number close to -1 from the left, we get a negative number in here. And then if we were to cube that, we would still get a negative number. Yeah, and that negative number is getting smaller and smaller in the negative direction. And so this tells us that our limit's going to approach negative infinity. And we see that with this similar limit here. The limit of 1 over x as x approaches 0 from the left. This limit is getting bigger and bigger in the negative direction. Okay. And we see the same thing for these examples as well, and you can compare them with the other limits in that figure. Similarly, here are some limits involving exponential and log functions that we saw in previous sections. And so we'll use these in some of our limits today. But just a reminder that the limit of e to the x, as x gets bigger and bigger, is just infinity. That limit's going to get bigger and bigger. But the limit of e to the x, as x approaches negative infinity, is going to get smaller and smaller. All right. And here's another example, comparing with this figure here. So as you can see, we have the limit of 2 times our exponential function here. X is going to get closer and closer to infinity, so we have 2 times e to the 3 times infinity, which is just 2 times e to infinity. And we saw that here, that's just going to get closer and closer to infinity, or just get bigger and bigger. Similarly, we have 4 times e to the negative 5x. Plugging in a positive infinity here, we still get e to the negative infinity. And we saw that that limit approaches 0. It's going to get smaller and smaller. Right? Similarly, the limit of ln x plus 4 as x gets closer and closer to infinity becomes ln of infinity, and that is equal to infinity, as we see in figure C here. All right, so that was just a brief refresher of these limits that we saw in previous sections and will be helpful in some of the examples that we'll look at today. So remember, if we have a limit like this here, where the limit of f of x is equal to 0 and the limit of g of x is equal to 0 as x approaches some number c, we have what's called indeterminate form. So we get 0 over 0. And so in this case, we can't use our quotient rule, or not our quotient rule, but we can't use the quotient property that says we can look at the limit of the numerator and the denominator separately. So this does not apply because if you remember, in section 2.1, we said we can only do this if this denominator here, if this limit does not equal to 0. But we know that when we have indeterminate form, it will in fact equal 0. So if we're dealing with this indeterminate form, the limit may or may not exist. And in some cases, we can do an algebraic simplification to get out of this indeterminate form, but when we can't, we'll turn to L'Hopital's rule. And that is this here. So if we have, for a real number c, if we end up with indeterminate form when looking at this limit, what we can do instead is take the limit of the derivative of our function f over our derivative of our function g of x. Now, this theorem remains valid if this is replaced with as we approach x from the left, from the right, or as x approaches infinity from the right, or sorry, positive infinity or negative infinity. Okay, so this can be generalized to all of these cases here. Now, for example here, let's say we have this limit. We know that if we were to plug in 2 for x here, we would end up with 0 over 0. So this is currently in indeterminate form. But if we factor this, we're doing an algebraic simplification, right? So we'll get x minus 2, x plus 2, and then the x minus 2 in the numerator and denominator will cancel. And so we're just left with the limit of x plus 2 as x approaches 2. And so we end up with 4. So in that case, we were able to do an algebraic simplification and evaluate this limit. Additionally, we can use L'Hopital's rule because we have indeterminate form here. So what this says is we're going to take the limit of the derivative of our numerator over the derivative of our denominator. So the first thing we're doing is taking the derivative of this guy, and we know that's just going to be 2x by our power rule, and we also know the derivative of this guy is just going to be 1. So now we'll take the limit of that, and we also end up with 4. So let's look at some examples of this. We want to evaluate this limit here, and we can already see that as x approaches 4, we'll get this here, which is equal to 0 over 0, so we have indeterminate form, right? So that tells us we need to use L'Hopital's rule. So we want to evaluate this guy, and by L'Hopital's rule, we know that this is going to be equal to the limit of the derivative of our numerator over the derivative of our denominator as x approaches 4. So we'll evaluate the derivatives. Be careful with this one because e to the power 4 is just a constant here. So the derivative of that guy is 0. And so we'll get e to the x on the top. And then in this case, we know the derivative of this is just going to be 1. Alright, so then we get e to the 4 over 1, which is just e to the power 4. So that is our limit of this guy as x approaches 4. Alright, now something to just be cautious of. When we're using L'Hopital's rule, this represents the derivative of f of x divided by the derivative of g of x, but we're not taking the derivative of this quotient here, so just got to be careful with that. And like we mentioned before, when we have indeterminate form, we're not going to use our quotient rule. We're going to use L'Hopital's rule. Alright, so let's look at another example here. we know that this is going to end up being this here. We know that ln of 1 is 0, and then we have 1 minus 1 cubed, which is 0. So we do have indeterminate form, so we'll use L'Hopital's rule. So if we want to evaluate this limit, we can just take the derivative of these functions separately. As x approaches 1. Alright, and note we're not taking the derivative of this quotient, we're taking the derivative of each of these guys separately, then evaluating the limit. So, we know the derivative of ln x is 1 over x. And then to find the derivative of this guy, we're going to be using chain rule. So we'll evaluate the derivative of our outside function. So this 3 will come down in front, and then we get to the power 2. So we get 3 times x minus 1 squared. So the derivative of the outside function evaluated at the inside function. Then we need to multiply by the derivative of our inside function, which we know is just 1. We're looking at this as x approaches 1. Alright, so let's do some simplification. We have 1 over x divided by this, which is the same as 1 over x times the reciprocal. So now we're looking at the limit of 1 over 3x times x minus 1 squared as x approaches 1. So we can see that as x gets closer and closer to 1, this gets closer and closer to 0, and our denominator as a whole gets smaller and smaller, which makes this whole fraction here bigger and bigger. And we saw that in section 2.1, that as we have a constant in the numerator and as our denominator is getting smaller and smaller, this actually gets bigger and bigger. So our limit of this guy as x approaches 1 is going to be equal to infinity. And I believe this is by theorem 1 in section 2.2. All right. Now let's look at another example here. This is an example where L'Hopital's rule may not be applicable. So in this case, let's look at this limit here as x approaches 0. So we know that this is going to be equal to 0 over e to the power 0, and e to the power 0 is just 1. So in this case, we actually get that our limit is equal to 0. And so this is not an indeterminate form. So in this case, we can't use L'Hopital's. Right, so we have to be careful in these instances. So in this case, our answer is just 0. And something to note here, that if we were to use L'Hopital's rule, so let's just try it out. So we're going to take the derivative of the top and bottom functions separately. We end up with the limit of 1 over e to x as x goes to 0. So we get 1 over e to the power 0, which we just said was 1, so we end up with 1. And so we actually would not get the correct answer if we did try to use L'Hopital's rule. So this is incorrect. Okay, so that brings us to this warning here. We always need to check to see if L'Hopital's rule applies before we can use it. So as we saw in all of the last examples, the first thing that we're doing is making sure that we do have indeterminate form before using L'Hopital's rule. All right, so let's look at this example here. So what we need to do first is check to make sure that we can use L'Hopital's rule. So here we'll get e to the power 2 times 0 minus 1 minus 2 times 0. over all over 0 squared. So e to the power 0 is going to be 1, and this one is equal to 0, so we just have 1 minus 1 on the top and 0 on the bottom. So this is 0 over 0, so we can use L'Hopital's rule. So we want to evaluate this limit as x goes to 0. So using L'Hopital's rule, we'll take the derivative of the function in our numerator and our denominator separately. Alright, so in this case we need to use chain rule here. So we're going to take the derivative of our outside function, which is e to the 2x, and then times the derivative of our inside function. Our inside function is 2x. So we'll get e to the power 2x times the derivative of 2x, which is 2. The derivative of this minus 1 is 0, but then we have this minus 2x here, and the derivative of that is 2. Derivative of x squared is going to be 2x. And we're looking at this as x approaches 0. Alright, but notice something. If we were to evaluate this, we would get e to the power 0. And there's a 2 multiplying that. Minus 2 over 2 to the power 0. Right. We know that e to the power 0 is 1, so we get 2 times 1 minus 2. So we end up with 2 minus 2 over 2 times 0, which is 0. And so we get indeterminate form again. So what we're going to have to do is do L'Hopital's rule again. So we're going to take the derivative of this, I'm just writing the 2 in front of e to the 2x because we're multiplying it by 2 here. And then we need to take the derivative of our denominator as well. Alright. Okay, so we're going to take the derivative of this guy. So we just have this constant multiple out front, so that 2 will stay there. And then remember we have to use chain rule again. Our outside function is e to the x, and our inside function is is 2x. So the derivative of our outside function is just e to the 2x, and the derivative of our inside function is 2. Then the derivative of minus 2 is just 0. And the derivative of 2x on the bottom, that's just going to be 2. Alright. Another thing we notice is we have 2 2's that cancel. We have 1 2 in the top and 1 on the bottom. So we end up with 2e to the 2x, because this 2 is still here, so multiplying e to the 2x. Alright, so now let's evaluate this limit. We'll get 2 times e to the 2 times 0. So we just end up with 2, since e to the power 0 is 1. Alright, so that is our answer. So we can use, and we do have to use L'Hopital's rule multiple times if we ever get indeterminate form as we're evaluating. Alright. So L'Hopital's rule also applies for one-sided limits. In this case here, we have the limit of this function as x approaches 1 from the left. So for example, we would have x getting closer and closer to 1. So here we could have ln of 0.99999. And so this would be 0.99999, and so on. So we're just getting really, really close to 1 from the left. And as we're doing this number is getting closer and closer to 0, because ln of 1 is 0. And then this guy's also getting closer and closer to 0 as we get closer and closer to 1. So we end up with indeterminate form 0 over 0. So we're going to use L'Hopital's rule. and evaluate this limit. So we're going to take the derivative of ln x and the derivative of x minus 1 squared. Alright, we know that the derivative of ln x is 1 over x. And here we have to use chain rule. So our outside function is a power function to the power 2. So that 2 is going to come down in front, and that is being evaluated at the inside function x minus 1. Then we have to multiply by the derivative of the inside function, which is just 1. Alright, so then simplifying this a little bit, we're going to multiply by the reciprocal. So we're looking at the limit of 1 over 2x times x minus 1 as x approaches 1 from the left. Alright, so remember we're looking at approaching 1 from the left. So we're to plug in a number super close to 1, but approaching from the left, so like 0.99. We see that this number is negative. And so this is actually, the denominator is a really small number, but a really small negative number, right? Since this is negative, this will make our whole denominator negative, and negative times a positive is negative, and this number is getting really, really small as we're approaching 1, okay? Because this is getting really, really close to 0. Alright, so we know that if we have a fraction like this and we're dividing by a really small number, our limit's going to get bigger and bigger, and in this case it's going to get bigger and bigger in the negative direction since we're dividing by a really small negative number. Alright, now let's look at an example for L'Hopital's rule for limits at infinity. Right? We saw that we can use L'Hopital's rule when we have a limit of this form as well. So let's just check to make sure that this is in fact in indeterminate form. And we're looking at as x approaches negative infinity, so this here. So in this case, this is where it's useful to remember what these limits are. As we saw in the beginning of this video, e to the negative infinity is going to be equal to 0. So this goes to 0 here. So we just get ln 1 on the top, and then e to the negative infinity, we just said that was 0. And remember, ln of 1 is 0. So we do have indeterminate form, so we'll use L'Hopital's rule. So this is the limit we want to evaluate, and we'll do so by taking the derivative of this guy on the top and the derivative of e to the x on the bottom. Alright. So we know that the derivative of ln x is 1 over x, but we have this inside function plugged in for x, so we're going to use chain rule. So it's going to be the derivative of our outside function, ln x, evaluated at the inside function. So 1 over 1 plus 2 e to the x. And then we need to multiply by the derivative of our inside function. Derivative of 1 is 0, and then we have this constant multiple times e to the x. So we get the constant multiple times the derivative of e to the x, which is just e to the x. And we get e to the x on the bottom as well, because the derivative of e to the x, like we said, is e to the x. Alright, so let's simplify this a little bit. We have 2 e to the x over 1 plus 2 e to the x in our numerator here. And then we're dividing by e to the x, so that's going to be the same thing as multiplying by the reciprocal, so 1 over e to the x. Okay. As we can see, these guys will cancel here. So we'll get 2 over 1 plus 2 e to the x. All right. Now evaluating this limit, remember we just saw that as the limit of e to the x as x approaches negative infinity is 0. So this guy here is going to go to 0. And so we're just left with the limit of 2 over 1 as x goes to negative infinity. So this just is equal to 2. All right. Now we can also apply L'Hopital's rule to this indeterminate form when we have infinity over infinity. In section 2.2, we discussed certain techniques for evaluating limits of this form here. And in this case, for each of these limits, we have indeterminate forms, so we get infinity over infinity. And so when we get indeterminate form of this form, we can use L'Hopital's rule. And we'll look at an example of that here. So evaluating this limit, we'll get ln of infinity, which we saw in the log and exponential limits above at the beginning, that will actually be equal to infinity. And then we have infinity at the bottom, so we get infinity over infinity here. So this is in indeterminate form. And so we use L'Hopital's rule in this case. So to evaluate this guy, we'll take the derivative of ln x and the derivative of x. So this is going to be equal to 1 over x over 1. So we're just evaluating this limit. So we end up with 1 over infinity, and we know that if we have something of this form where we have a constant in our numerator and we're dividing by a really, really big number, we know that this whole thing is going to be smaller and smaller, so that limit is going to be equal to 0. All right. So yeah, we can use L'Hopital's rule whenever we have an indeterminate form like this as well. All right, so the last thing we're going to look at is horizontal asymptotes and L'Hopital's rule. So for this example, we want to find all of the horizontal asymptotes of this function here. And just as a refresher, recall that if we want to find the horizontal asymptotes, which I'm going to abbreviate as HA, we need to look at the limit at positive and negative infinity. So we went over this in previous sections. So what we'll do is we'll look at each limit individually. So we're going to take the limit of our function as x goes to positive infinity. So in this case, we'll get infinity squared over e to the minus infinity. So we'll get infinity over 0. Now we can't divide by 0, but we're not in indeterminate form. Okay, we would either need 0 over 0 or infinity over infinity. So what we're going to do in this case is do an algebraic simplification. Looking back at our function, this can be written as x squared times e to the positive x. Right? So just writing this as a positive exponent brings it into the numerator. So we're going to look at the limit of this guy as x approaches infinity. So in this case, we'll just get infinity squared, and then e to the power infinity was infinity. We again saw that in the limits we looked at the beginning for our exponential and log functions. And so this is just equal to infinity. So in this case, we have no horizontal asymptote here. And that's fine, we'll just state that. And then we're going to look at the limit of our function as x approaches negative infinity. Now in this case, we have infinity squared, which is just infinity, and then we have e to the minus x as x approaches minus infinity, so this becomes e to the power infinity, and we saw that that was equal to infinity, right? E to the power negative infinity is 0, but to the power positive infinity we get infinity. So in this case, we have an indeterminate form, so we're going to use L'Hopital's rule. All right. So let's take the derivative of x squared and e to the negative x as x approaches negative infinity. So you know the derivative of x squared is just going to be 2x, and here we have chain rule. We're going to use chain rule again because our outside function is e to the x and our inside function is negative x. Okay. So we're going to take the derivative of our outside function evaluated at our inside function, which is just e to the negative x, and then we have to multiply by the derivative of our inside function, which is going to be negative 1. All right, so sorry, oh yes, okay, just making sure that was correct. So we have 2x over minus e to the minus x. All right, but what threw me off was that we actually need to use L'Hopital's rule again. Plugging in infinity or minus infinity here, we'll get minus infinity, and then plugging in minus infinity here, we get e to the positive infinity, but minus. So we have to use L'Hopital's again. All right. So we're going to look at the derivative of 2x, we get 2, and then the derivative of minus e to the minus x. So remember, we're going to have to use chain rule again. So we're going to look at the derivative of minus e to the minus x, and then multiply by the derivative of our inside function, which would be negative 1. All right, so then we end up with this limit here. And remember, we're just going to get 2 on the top, but the limit of e to the minus x as x approaches infinity is just going to be infinity. And remember, when we're dividing a number by a really big number, we're going to get a really small number. So this here, 2 over infinity, is getting closer and closer to 0. So this tells us we have a horizontal asymptote at y is equal to 0. Alright, so that's it for this video.